Hey folks, so welcome back. I'm still a fish. I think that's just gonna be a thing for a little bit just because I'm tired. And I can only imagine how tired you all are. But anyway, yeah, let's talk about some factor analysis terms. Right. So we got a lot of terms. Um, and so this one's gonna kind of feel like a top tens list. So we have the observed correlation matrix. Uh, and this is that matrix that's like a box. Same way that when you display multiple correlations, it looks like a tic-tac-toe board. Yeah, a grid. It's a grid. It's a matrix of correlations between all of your items. So if you have a questionnaire with 10, it's going to be a 10 by 10. Next is the reproduced correlation matrix. So this is the correlation matrix that is reproduced by the factor model. It's the estimate, so to speak. And the residual correlation matrix is the difference between your observed and reproduced correlation matrix. And the greater the difference between your observed data and the reproduced data indicates, well, that your model is bad and you should feel bad. Oh, sorry, I'm being facetious. But greater differences between what is observed in our real data versus what our model tells us our data should look like indicates a mismatch. And either your model is incorrect or your data are. And ideally, you would have a model that fits your data and explains your data well. And in that instance, you would see very few differences between what you observed and what you got after you run your model. So extraction refers to the two steps, or at least these two steps in the process. So step one is pick your method. It's the whatever factor analytic or PCA method you choose. There are dozens of these, but this is the step where you like fit your model. And the extract process is where you suck out the data, so to speak, from your model so you can use it on other things. I have very mixed feelings about this process because although it is common, there are some serious statistical issues with it that boil down to making your data look, or making the factors look more precise than they actually are. But that is beyond the scope of this class. So the key things to know here is that extraction is the process of getting estimated results out of your model. Okay. Loadings are a measure of the relationship. They're pretty closely analogous to correlations. And it's the correlation between each individual item and the overall factor. So that latent thing. And the size, that Greek pitchfork thing, is effectively what those are in the common factor model. They are describing how closely related the individual item is to the overall factor. Higher loadings correspond to closer relationships. So if you have a high factor loading, what that means is that scoring higher on that item is really indicative of having a higher score on that factor. All right, so for the handful of linear algebra folks in the room, here is the essential process for how all this data works together. So you start by spinning in, generating your matrix. And your matrix is a big Excel spreadsheet where you have all the variables that you're interested in seeing how they relate. So each individual question on your questionnaire, and each row is a respondent. And what we do with that data matrix is we essentially convert it into a correlation matrix, which is approximately the factor loading matrix plus a transposed matrix, which then tells us how to get the, sorry, let me back up. Okay, so this is where the big disconnect in this class comes in, to be honest, and it's a little challenging to teach. And I'm telling you this because I think y'all are adults, and this class can go super technical, as you can see here, but there's also serious qualitative aspects. And so yeah, all right. So we go from our data matrix to our correlation matrix. Data tells us is what we start with, and the correlation matrix describes how all the questions relate to each other. So a highly internally consistent matrix is going to have lots of high correlations, which in turn is approximately our factor loading matrix. We also have a transposed matrix that allows us to relate our factor loadings to our overall data structure. And these combine to the correlation matrix that our model estimates. All right? Our factor model is giving us an estimate using our data. And our observed correlation matrix, so that's like the real one, based on our data, we compare that to the estimated correlation matrix that our model gives us. And any discrepancies between those indicate measurement error, model misspecification, and they are the residual matrix. All right, so let's look a little deeper into the factor loading matrix. So you know what? I'm going to have this live in the lecture notes. All right, so factor scores. So the factor score model, or the factor model, is used in common practice to generate a combination of the items to create a single score for that factor. It's like a weighted average of your items based on your model. While the factor coefficient matrix are those coefficients we use to create the factor scores. They're the like weighted coefficients. Think like regression coefficients. All right. Now rotation is a way to mathematically turn our data so that the factors are easier to interpret for people. Now there are two kind of big ones that you'll hear a lot, and there are subtypes, but the big ones are orthogonal and oblique. So orthogonal rotation is very popular, and what it does is it assumes that your factors, so the if you have more than one, are uncorrelated. So it forces the data to be at right angles from each other if you were to plot it. Now, is that true in reality? Probably not. An oblique rotation allows the factors to tilt. so that you can have factor 1 correlated with factor 2. All right. So, oh, apparently I summarized this here. How convenient. So, orthogonal keeps our factors independent, so they are uncorrelated with each other by design, regardless of the reality of the situation. And there's only one matrix. It is nicely rotated, and this is interpreted as the rotated loading matrix. Oblique, very similar. There are tons of different rotation methods. But at the end of the day, what oblique allows is for, say you have a test with multiple measures on it, multiple factors, they're allowed to be related to each other. So if we were to look at the big 5 factor model and look at neuroticism and conscientiousness, we would expect, depending on the theory, that they'd be slightly negatively correlated. So higher levels of neuroticism on average would be associated with slightly lower levels of conscientiousness because they have an overlapping chunk of items on impulsivity. All right, so here are the important matrices. Factor matrix. This describes the correlation between our factors. It tells us how our data are related to each other, our big overall data. The structure matrix. That tells us the correlation, so the associations between our estimated factors and the variables we used to make them. Sorry, there's cat chaos. And the pattern matrix. So this is the one you interpret, okay? This shows us the unique relationship between each factor and an item uncontaminated by overlap between factors. In other words, this is the relationship between your individual item and the factor that is not shared by other factors. This is the matrix you interpret, in other words. Okay, so simple structure. So this refers to the ease of interpretability of the factors, like what they actually mean. And this is achieved when an item loads highly, so its factor loading is closer to 1, depending on how you fit your model, on a single factor when multiple factors exist. So see that previous slide. So and it also has a lack of complex loadings, items that load highly on multiple factors. I've got an image coming up here. Okay, so simple structure is this data structure where we've got 2 factors. So this is the one on the left, where all the arrows map nicely. We've got items 1 through 3 are only associated with factor 1, and items 4, 5, and 6 are only associated with factor 2. Now there are some implicit arrows here, that force our model to be uncorrelated. So factor 1s, you could pretend that it does have arrows to 4, 5, and 6, but those arrows are zeros. It's saying it's unrelated. Now a complex factor structure means that we have some arrows that hit both boxes, and here the complex factor structure is because question 3 is related to both factor 1 and factor 2. It makes it harder to interpret. It gives major headaches if you're going to use factor extraction techniques because it's wonky, folks. Cool. Okay, so that's it for our hot mess of terminology. Thanks for hanging in there. I realize that this is like a super technical little chunk, and I recognize that, so I'm going to be gentle about it on assessments. Okay. I'll see y'all later. Bye.